Hello, chemists. This is Miss Placino, and you are watching lesson 1.4 on separation of a mixture. In today's lesson, we're going to be talking about how to separate mixtures using different pieces of equipment. Now, my guess is that you're already pretty familiar with how to separate mixtures, at least pretty simple ones. So we just need to give you some pieces of equipment and some terminology to kind of tighten up your explanations a little. So we've got a couple of goals for today's lesson. First, identify different pieces of equipment used to separate mixtures. There's going to be 6 different pieces of equipment or techniques that we use. And devise a separation scheme for mixtures containing 3 or more components. All right, so let's get into the lesson. Let's say that you've got this pile of coins, and because you have OCD, you'd much rather it look like this. How can you accomplish this? I'm guessing some of you are thinking, well, you can just go through and manually pick out the different coins and stack them up into piles. That sounds like a great job for your younger sibling. You might be thinking, oh, I could get a coin sorter, and that way I could go through and just kind of throw everything into that instrument, and then it would stack up the coins for me. If you really think about what's happening in both cases, you are using physical properties of the coins to separate them. For example, if you're picking things out by hand, you might go after the pennies first because they're a different color. Then you'd have to use size to separate the dimes, the nickels, and the quarters. And in fact, size is how a coin sorter works. They're all different diameters and slightly different thicknesses. So the coin sorter knows what coin it is based on its dimensions. Whether you do this by hand or you invest in a coin sorter, you are making physical changes to that pile of coins. You're not changing the chemical makeup of any of the coins. You are simply just arranging them differently. They're in a big, messy pile on the left, and you want them in nice, orderly stacks like we have on the right. The key to all of our separation techniques is that since mixtures are only physically combined, meaning the substances are in close proximity or touching each other, we can use physical techniques to separate them. So as we go over the different pieces of equipment, we'll talk a little bit about the physical properties that are being used to separate the components of that mixture. All right, so let's get into our pieces of equipment. Up first, we have the filtration funnel. Really easy apparatus to set up. You've got this Erlenmeyer flask. You've got a funnel, and inside the funnel, you've got a piece of filter paper. What phases of matter might we be able to separate with a filtration funnel? Hopefully you're thinking solids and liquids. Really, the idea behind how this works is the solid would get stuck onto the filter paper while the liquid could pass through. Separation of a mixture. This works really well if you have solids that do not dissolve in the liquid. In other words, that mixture needs to be heterogeneous. We need visibly distinguishable parts. For example, if you had a mixture of sand and water, a filtration funnel is a great tool to separate them. The pieces of sand, because they don't dissolve in water, will stick to the filtration funnel, while the water will pass straight through. This would not work for something like salt water. Salt dissolves in water and forms a homogeneous mixture. So when you go and pour salt water through the filtration funnel, the salt will not stick to the filter paper. It will pass through with the water. You would need a different tool if you wanted to separate salt water. Our second piece of equipment is a separatory funnel. So in a separatory funnel, we've got 2 different liquids. I'll call them 1 and 2. So our separatory funnel will separate liquids based on density and polarity. Now, we talked about density in the previous lesson. You've probably seen oil floating on top of water before. Oil has a lower density, so it is going to float if the other liquid present is water. But why don't they mix in the first place? That has to do with polarity, and that's a topic that we'll be kind of revisiting multiple times throughout the school year. But basically, you've probably had like oil on your hands before. If you want to get it off your hands and you just rinse with water, it's really, really difficult to get oil off that way. The oil doesn't want to stick to the water. It's because it has a different polarity, and substances with opposite polarities do not mix together. So in this case, the opposite polarities allow this really nice division to form between the two liquids. I would open up the valve, I could drain the first liquid out and then stop it so that the second liquid is caught in the separatory funnel. This works if we're talking about a heterogeneous mixture. Something like oil and vinegar could be separated this way. Oil and water would work as well. Water and vinegar would not work. Water and vinegar have the same polarity, so they would dissolve into one another and form a homogeneous mixture. This needs to be heterogeneous. Even though vinegar and water have two different densities, since the polarity is the same, they will mix, and suddenly we cannot use this tool to separate that mixture. This piece of equipment is called a distillation apparatus. So let's say we've got a mixture of, well, let's go ahead and use rubbing alcohol as an example. Rubbing alcohol is usually, at least 50% water, and then you've got the rest of it is your alcohol. So what we would do is take a heat source, like a hot plate, take our mixture, and we'd heat it up. The distillation apparatus is going to separate liquids based on their boiling point. In a mixture like rubbing alcohol, we've got water with a boiling point at 100 degrees Celsius, and isopropyl alcohol, I can't remember off the top of my head, but it's somewhere between 70 and 80 degrees Celsius as its boiling point. So as the substance heats up, the isopropyl alcohol is going to evaporate or vaporize, turn into a gas as the substance starts to boil, and it's going to travel through this tube. Here, we have cold water going in and cold water coming out. It's kind of tough to see at first glance, but if you look, the water that's coming in and out never comes in contact with the tube that in this case, alcohol vapor would be in. What effect is that going to have temperature-wise on that part of the distillation apparatus? Yeah, it's going to make it cold. And when that warm vapor touches the cold glass, it's going to condense, and then hopefully a pure substance, maybe in this case the alcohol, will be collected in the other flask. This is the way to separate a homogeneous mixture of two liquids. Heterogeneous, we would use the separatory funnel. If they do mix together, we can use the distillation apparatus. This is also a tool that we could use to separate solids dissolved in a liquid. So we gave the example of salt water not being separated by a filtration funnel. We could use the distillation apparatus, boil away the water. We'd be left with the salt sitting in the flask that's on a hot plate, and we'd collect the water in the other flask. Please go through and put a star next to those three different pieces of equipment: the filtration funnel, the sep funnel, and the distillation apparatus. Those are probably the three most common pieces of equipment that get used in intro chem for separating mixtures. We have the magnet, which I'm sure you know is going to attract magnetic materials. This is particularly useful if your mixture contains iron. It's probably the best example or the most common example of a magnetic substance. All right, our last two are kind of more advanced separation techniques. You might recognize this piece of equipment from bio. It is a centrifuge. A centrifuge also separates solids and liquids. You might be thinking, well, why do I need a centrifuge? I've got the filtration funnel, or vice versa. Key is our solids have to be very small. We'll talk more about why in just a moment. A centrifuge works by you put your mixtures into the centrifuge tubes, close it, turn it on, and it's going to start spinning really, really fast. And as it does it, the mixtures that are in the tube should separate out based on density. So the most dense stuff is going to sit at the bottom of the tube. The lower density substances in your mixture will be up towards the top. This really is only helpful when we have extremely small solids. If you're talking about separating sand from water, you wouldn't turn to the centrifuge. The filtration funnel will do the job quite nicely. Putting your sand and water mixture into the centrifuge is akin to killing a fly with a bazooka. Yes, you can do it, but why would you? There is a much simpler tool that you could use. We'll use a centrifuge if it turns out that our solid that is trying to be separated is so fine and so powdery that it just passes through the filtration funnel. We would use the centrifuge in that case because our simplest tool did not work. All right, last but not least, chromatography. In AP chemistry, they talk about it in terms of paper chromatography. This happens to be a column, but it's going to work on really the same principles. So I'm going to explain what chromatography is first, and then we'll go back and try to make some sense of it. Okay, so in chromatography, we're going to separate substances based on their attraction to the material in the column. So a lot of times you'll see kind of the quintessential examples of your separating ink. If you have high quality black ink, it is actually composed up of 3 colors, red, yellow, and blue. So I could take my sample and I could pour it into the column. And the column's been packed with some material. There are different materials you put in the column. Then I'm going to add more liquid or my solvent to kind of start to force the ink, force the sample to make its way through the column. And I would continue to add more and more until I get all of this stuff out of there. This advanced separation technique works well for homogeneous mixtures. And you might be thinking, well, wait a second, don't we have the distillation apparatus for that? Why would I bother with this? Well, if you've got really similar boiling points for your substances, you might not get good separation from distilling it. So you might have to use something like chromatography. Again, this is an advanced technique, something that you probably wouldn't run into until you're like taking a college chemistry lab course. All right, so let's talk about this attraction to material in the column. I've got 3 different chemical compounds represented by the 3 different colors. What I'd like you to imagine is we're on the 9th floor and you're at one end of the hallway and I'm at the other. And it's after school, so I can't really tell you what to do, but I'm motioning for you to come towards me. And in between you and I, there are just a pile of people. And it turns out that the hallway is packed with your friends. So I'm telling you, come on, let's go. And you are trying to weave your way through your friends. And you haven't seen them all school day, so they want to stop, they want to talk to you, they want to hear about your day, they want to show you funny stuff that they found on the internet. It's going to take you a while to move through there because you are friendly with all the people who are there. It's like being attracted to the material in the column. You move very slowly through it. If you imagine that same scenario, except I've filled the hallway with complete strangers. Yeah, I mean, you're not going to be able to just sprint right through them, but you are probably not going to stop and talk. You're going to get through that hallway much, much faster because you are not attracted or interested in what's packing the hallway, or packing the column. The same thing applies here. I've got my black sample of ink composed of different colors. And we can see that yellow came out first. So what does that tell us about the attraction the yellow molecules had to the stuff in the column? Yeah, they're not particularly attracted to what's in the column. They're not interested. They were able to make their way through pretty quickly. On the opposite end of the spectrum, we've got the blue ink. The blue ink took the longest to come out of the column. It must have been attracted or interested in the molecules that are present or the material that is present in the column. So that's really how chromatography works. The stuff that comes out first is not attracted to what's in the column. The stuff that comes out last is very attracted to what's in the column. Again, advanced separation technique, but I figured it would be interesting to introduce it. Okay, so to summarize, we've got a substance like water. We can put it into our distillation apparatus or any separation tool for that matter, and boom, we come out with oxygen and hydrogen molecules. Is that right? No, of course not. This is really 100% incorrect. What we're describing in this picture, the series of pictures, is a chemical change. We're taking water molecules and turning them into hydrogen and oxygen elements. All of the techniques that we talked today, whether it's something really simple like a filtration funnel or something more advanced like a centrifuge, cannot be used to separate compounds into their elements. That requires a chemical change. Everything we've looked at today has just been physical properties being exploited to separate mixtures. So please, please, please remember separation, and I know I'm kind of beating this to death, but uses physical properties. All right, so let's try out a, I think, kind of challenging mixture to separate. You've got salt, sand, and iron filings. Iron filings are just like little pieces of iron. Like imagine like sharpening your pencil and like all the nastiness that produces, except this is iron. What I'd like you to do is pause the video and see if you can brainstorm in a technique or a series of steps to try to separate out these three things. This is a tricky one. Hopefully you've got a separation technique kind of plotted out. I would say first and foremost, grab the magnet and get rid of the iron. We know that iron is magnetic, salt and sand, on the other hand, are not. Salt and sand. How am I going to get those separated from one another? They're both solids. Some of you might have come up with this. Add water. Tricky. What's going to happen when you add water? Yeah, we're going to dissolve the salt. Then I can use the filtration funnel. That will separate out the sand. It will get stuck to the filter paper, and the salt water will pass through. And then last but not least, we can use the distillation apparatus. Distillation. And we can separate the salt and water. How'd you do? Yeah, separation of mixtures. Again, I bet in your mind you can kind of imagine how you would do it. You just want to work on putting the different pieces of equipment to your ideas. We'll practice this more in class. All right, thank you for tuning in, and I hope you found this helpful.